present Chapter 5, Equipment Sizing and Cost Estimation. For the first design summary is for the R101, that is the reactor 1. The specifications are the volume, diameter, height, thickness and weight of the reactor. So the volume of this reactor is 480 meter cube, diameter is 231 inches, height is 695 inches, thickness is 7.16 inches, and the weight is 1.3 million pounds. So for the following designs, we will include every of these specifications. So this is the design summary of the separator 1. Next is the design summary for reactor 2, which is R102. The specifications are the same. And this is the summary of specification for compressor. The horsepower of the compressor is 3,826 horsepower. Operating efficiency is 75%. Brake horsepower is 2,869. Operating efficiency of the motor is 95%, and power consumption is 3,021 horsepower. The design summary for separator V101 is also the same. Design summary for distillation column also includes volume, diameter, height, thickness and weight. These are the other distillation columns, T101 and T102. Next is the summary of specification of heat exchanger. For the heat exchanger 1, we calculate the area and we get the BWG, wall thickness, shell diameter, length, outside diameter, number of tubes per pass and tube pitch. So for the heat exchanger 1, the required area is 317 feet square, BWG 16, wall thickness of 0.065 inches, shell internal diameter of 15.25 inches, length of 20 feet, outside diameter is 0.0833 feet, number of tubes per pass is 61, and the tube pitch is 1.25. So for the following heat exchangers, dimensions and specifications are as follows. So for heat exchanger 5 and heat exchanger 6, we also calculate the same the specification for the heat exchangers. And lastly, this is the summary of specification for heat exchanger number 7. The title that I am going to present is Chapter 6, Process Control and Safety. In control systems, the control system is used to maintain process at desired operating level within design constraint. The trade-off between economics and controllability are as crucial because the design based on economy alone is risky, resulting in difficulty to control plant, off-spec product, excessive use of fuel, and etc. The design of a control system for a chemical plant is guided by the objective to maximize its profit. The 4 constraints required for special consideration are: first, product specification. To meet the expectation of the customer, the product quality and rate must meet specification. Next is the safety. The plant must be operated safely to protect the well-being of the plant operators and the personnel and the nearby communities. Next is the operational constraints. This is related to the desired operating range of the process units. And the final one is environmental regulations. Processing plant comply with constraints on the air and water quality as well as waste disposal. These are the qualitative design procedure for plant-wide control by Lubian, Tyrus and Lubian. The steps in the design procedure are: determining the control degrees of freedom, establish the energy management system, set the production rate, control the product quality, and handle safety, environmental and operational constraints, fix the flow rate in Aries recycle loop, and control vapor and liquid inventories, check the component balance, control the individual process unit, and optimize economics and improve dynamic controllability. This is the overall of the ENID of our processing plant. The mainstream is both with thick line, and the flow is from here straight until the end. Next is the hazard studies. There are 7 points for the hazard study. The first one is identifies hazard operability and evaluates problem. Next, investigate the plant deviation from design intents. Following is the identifying problems, and when a solution becomes apparent, it is recorded as part of the hazard result. Avoid trying to find solutions which are not so apparent, because the prime objective of the hazard is problem identification. Next is assume that a hazard or operating problem can arise when there is a deviation from the design or operating condition. Actions to correct identified hazard or operational scenarios before a real incident occurs. And lastly, the primary goal is to identify, not to analyze or quantify the hazards in a process. The end product of a hazard study is a list of concerns and recommendations for prevention of problems, not an analysis of the occurrence, frequency, overall effects, and the definite solution. The success or failure of the hazard depends on several factors. First one is the technical skills and insights of the team. Second is the completeness and accuracy of drawings and other data used as a basis of the study. Third is the ability to learn, to concentrate on the more serious hazards which are identified. And the last one is the ability of the team to use approach and as an aid to their imagination in visualizing deviations, causes, and consequences. Lastly is the hazard study in process flow. The guidewords are more, less, no, reverse, more, less. These are the possible causes and consequences of process plant. Take an example. For the first one, more and the deviation is flow. The possible causes is the failure of the valve, and the consequences is high level in the reactor. So the action required to be taken is high level alarm.
This is the engineering drawing of the plant.